Hello everyone, and welcome to this first broadcast of a three-part webinar series that is being put on by the ACS Division of Polymer Chemistry. I'm Mike David, and I will be your host for today's broadcast, which is focusing on polymerized ionic liquids and nanostructured polymers. We will have two presenters today, Thomas H. Epps III, who is the Thomas and Kip Gutshall Professor of Chemical and Biomolecular Engineering and a Professor of Material Science and Engineering at the University of Delaware, and Yosef Iblad, who is a Professor, Associate Department Head, and Director of the Undergraduate Program in the Department of Chemical Engineering at Texas A&M University. Our moderator today is Mark Hillmeyer, who is the Chair of the Division of Polymer Chemistry, as well as a Distinguished McKnight University Professor of Chemistry at the University of Minnesota. And now, I'm pleased to turn the time over to Mark.
Thanks very much, Mike. It's really my honor to be the host of this inaugural webinar series and also to be the 2017 chair of the Division of Polymer Chemistry. In the Division of Polymer Chemistry, we're very focused on member benefits and bringing benefits to all of our membership. A lot of times this comes through our outstanding programming at national meetings and also through our distinguished workshop series. However, we recognize that many of our members actually every year are unable to attend a national meeting, so we thought we would try something to bring contemporary topics in polymer chemistry via the internet through a webinar series. So we're very thankful not only to the ACS for helping host this, but also for our first inaugural series and our two speakers today. So I'm going to introduce the speakers. What we'll have is two short presentations. There'll be a small gap between them, and then at the end we will entertain questions using the GoToWebinar interface, and I'll moderate the question answer session at the end. So I'm going to now turn it over to Joe, and he's going to give us our first 20-minute presentation for this inaugural webinar. Joe, please.
Well, thank you, Mark, and also it is an honor. I appreciate the invitation from ACS Poly and yourself to be one of the first presenters in this webinar series. Today, I will speak about polymerized ionic liquid, which is sort of a new class of ion-containing polymers, and I hope that my presentation will do a good job of complementing Professor Epps' following presentation. So before I tell you about polymerized ionic liquids, I'll just say a little bit about ionic liquids for the broad audience. Ionic liquids are typically organic-based salts with melting points below 100 degrees Celsius, and many are probably familiar with room temperature ionic liquids, which just means it's the same thing but with melting points below room temperature. So typically you'll see this on the lab counter as a kind of a viscous liquid. I'm showing here one of the first ionic liquids introduced, ethyl ammonium nitrate, by Paul Walden over 100 years ago, and some may be familiar with what's known as a Walden plot, which shows a lot of ionic liquids. The conductivity, the ionic conductivity of ionic liquid will scale pretty well with the viscosity of the liquid. Some more common ionic liquids today, if some of you are in this field, are typically heterocyclical ring structures like this one, the imidazolium-based ionic liquids. And some of the interest in ionic liquids in general have been used for green solvents, but more recently in electrochemical devices, energy devices such as batteries and capacitors. And the reason is because not only do they have high chemical and thermal stability and high ionic conductivity, but it's things like the wide electrochemical window and non-flammability and non-volatility that make them very interesting for battery applications. And when I say wide electrochemical window, when we think of water, we know that if you put 1 volt in water, usually can decompose water into gases of hydrogen and oxygen, whereas ionic liquids are known to go 5, 6, 7 volts without chemically decomposing. So this is very attractive for applications such as batteries and capacitors, where power typically scales with not only charge but also the voltage, so you can operate at much higher voltage windows. When we think of a polymerized ionic liquid, it would be advantageous to think about how do we incorporate these unique physiochemical properties of ionic liquids within a macromolecule. And here I'm just showing a cartoon depicting the ionic liquid in each repeat unit of a polymer. And here you could see, let's say, if you had a styrene-based polymer, you could think every repeat unit typically would have a covalently attached cation, which is typical of this ionic liquid family, and then a counterion that would be linked to that. That could be mobile. So these are typically referred to as single ion conductors. And the attractive feature about the idea of polymerized ionic liquids is that you just have a wide variety of chemistries that you can tap into for cations and anions, which make them very attractive. And as I'll show you later, by modifying this chemistry just a little bit, you can have significant changes in the physical properties of the macromolecule. And so there are several advantages here. One interest in polymerized ionic liquids is the versatility in chemistry makes this very different than ion-containing polymers leading up to this, where there sort of have been a limitation in some of the things that we've looked at, such as carboxylic acid or sulfonic acid-based ion-containing polymers. So this opens up a much broader field of chemistry. And then the other thing, by incorporating this into a macromolecule, you can think about now many other applications that people are looking into, such as polymers for carbon dioxide separation, where imidazolium TFSI is known to have much higher solubilities for carbon dioxide over other gases, or all solid-state devices such as batteries and capacitors and fuel cells. And so this has been some of the huge interest in polymerized ionic liquids. And I'm just showing here a reference at the bottom. This was really first pioneered by Ono in 1998. So still a very relatively new field. And there are still many chemistries that have not been explored in terms of polymerized ionic liquids, which makes the field very exciting. On slide 9 here, I'm just showing a typical polymerized ionic liquid. This is one that we've synthesized in our lab, and others have too. So you can see here that the backbone is a PMMA-like, polymethyl methacrylate. And here you can covalently attach a commonly known ionic liquid and imidazolium-based cation. And then just through ion exchange metathesis, we could look at a variety of different counterions. And we've done this, and others have too. And so here's a typical class of counterions, and they're fluorinated. This is typically what you'd see in ionic liquids. And what's interesting is you produce very hydrophobic polymerized ionic liquids, just like PMMA is very hydrophobic. But by changing the anion, you could drastically change the glass transition temperature. And probably what's interesting compared to other ion-containing polymers that you're used to is typically, let's say if you take typical plastic and you sulfonate it with a strong acid like sulfonic acid to make it an ion-containing polymer, that typically increases the glass transition temperature. In ionic liquids, it's a little different. Typically, when you functionalize typical plastics like styrene or PMMA, it will actually sometimes do the opposite because of the very bulky counterions and their weak electrostatic interactions will actually, instead of acting like an ionic crosslinker, it can almost act like a plasticizer and actually reduce your glass transition temperature. And you can also think about other anions. Here I'm showing at the bottom, if you think about halides or carbonates or hydroxide. And what's interesting is if you take the same polymer and do this ion exchange, you can actually go from something that's very hydrophobic actually to something that's very hydrophilic and can even be water soluble. So just by doing the ion exchange, you can have a significant impact on the hydrophilicity, not just the glass transition temperature. In slide 10 here, you can see this just shows you an example. If you look at all of these counterions on the same polymer, just the significant difference in the glass transition temperature, where the largest one here at the bottom, TFSI, this fluorinated one, has such weak interactions, ion pair interactions, that it'll have a TG that's even 100 degrees below that of just PMMA. That's a non-ion containing polymer. And you could just see this sort of scales with size. As you lower and lower the size and increase the ionic interaction of the ion pair, your glass transition temperature will rise. And then slide 11, you can see for the fluorinated anions that are hydrophobic, you could plot the ionic conductivity, and this is a property that would be a very high interest for batteries here if you couple this with lithium salt. You can see the properties of the ionic conductivity as a function of the inverse temperature of different counterions here. And again, as you see the glass transition temperature, as the glass transition temperature is lower and lower, that will increase the conductivity. So this is all done under a dry state where the ion mobility of these single ion conductors is very much dictated by the segmental motion of the polymer. So the lower the glass transition temperature, typically higher and higher the ion motion. And I know Thomas Epps will talk about this more in his presentation. However, you could think about other counterions here that I showed you on the slide previously that will actually produce very hydrophilic polymers, and the ion transport mechanism in these materials are very different. So here you can see the conductivity as a function of the relative humidity, and as you increase the relative humidity, you'll see the ion mobility will increase by decades. And this is just a completely different ion transport mechanism, and this is pretty similar to those you may be familiar with, things like Nafion or sulfonated polymers that have proton conductivity. This is very much a water-assisted process, not so much dictated by the segmental motion of the polymer chains. And typically, if you plot this conductivity versus temperature, it would follow an Arrhenius behavior, whereas the slide previously would follow VFT or WLF type behavior. For us, and I think many of you who are interested in putting these into devices, one of the things that we've thought about is things like block copolymers, and I know Thomas will talk about this more in his presentation. And really the reason for this is, let's say if you are thinking about things like hydroxide conductors, you want something for a fuel cell application. Typically homopolymers can be water soluble in liquid water, so you'd want to make functional membranes, and this is just one strategy in making a functional membrane. So one of the blocks of your block copolymer could be a polymerized ionic liquid containing block, and you can grow that chain, let's say after or before you would grow a typical commodity plastic like PMMA or polystyrene. And here just shows you an example structure of polystyrene and then our PMMA-based polymerized ionic liquid, where again we have a covalently attached cation. And the rationale for doing something like this would be to combine properties that you would see of the block copolymer and the polymerized ionic liquid. So we know block copolymers have great features such as nanostructured morphology, and that can produce high ionic conductivity channels. And then you can also incorporate the orthogonal properties, high mechanical strength for applications such as batteries and fuel cells, and be able to make very processable films that could be molded how you like for that application. However, you also, within the microdomains, you are putting in polymerized ionic liquids. And the attractive feature there, particularly for applications such as batteries, is that you're incorporating chemistry that has a very high electrochemical stability or high electrochemical window. So that's very attractive. And so if you look into the literature very recently, you'll see things like not only ionic liquids and polymerized ionic liquids in these applications, but now polymerized ionic liquid block copolymers. And it's really this broad chemical diversity which makes it interesting, because you can start to sort of optimize all of these properties in terms of ion conductivity, mechanical strength, electrochemical stability. And here I'll just show you a couple examples of some things of how block copolymers can impact ion conductivity. Here's an example, and here's the structure on the left. This is the morphology factor, which is a normalized way of showing the conductivity, normalized by the polymerized ionic liquid homopolymer conductivity and the volume fraction. And you can see as you go from cylinders to lamellae to network, and you remove some of these dead ends and go from a pseudo 2D to 3D network morphologies, you can see that normalized conductivity is increasing. And so the morphology type can have a significant effect on the ion conductivity. Here's another example where you can see that we've increased the side chain on the polymerized ionic liquid block from 2 to 11, and you can also see this has an impact on the mobility of the ion group within that microdomain, and that also can increase conductivity at a similar ion exchange capacity. And here's some work from Rachel Siegelman's group, and they also show something similar but much more quantitative. Here you can see a plot of the conductivity versus the channel size here, and you can see as the channel size increases, or you increase that mobility in the microdomain, you can see an increase in the conductivity. So you definitely see these are just several examples of how morphology can impact ion conductivity in single ion conducting PIL block copolymers. The other interesting feature here is now recently a number of people have shown that you can make these from a variety of different polymerization technique. Here is an example of nitroxide mediated polymerization, anionic polymerization, RAFT, ROMP, and also ATRP. And of course, I think probably in this field, this is still fairly new. Again, you have just the ability to really tailor properties not only from the monomer chemistry, but the cations and the anions available. And so there's almost a limitless number of chemistries that we could tap into. And this makes it interesting because if we change one thing, just the anion, this could be applicable to many different applications. So there's just a high versatility in applications because of the versatility in chemistry. A couple examples here. So the midazoleum TFSI here is well known to have high solubilities of CO2 over other gases. So some investigators have looked at these as membranes for CO2 separation. Also, several investigators have looked at doping these with lithium salts and using these as solid-state separators and binders in lithium-ion batteries. Also, you could think about different halides and think about water purification membranes. And then another application would be hydroxide as the counterion for application of alkaline fuel cells. And so since Thomas Epps will talk probably more about batteries in his presentation, I thought I would just use the rest of my time here to talk about this alkaline fuel cell application. And I also would like to point out this slide on the bottom is a recent highlight article where we have highlighted some of the recent results in the field on polymerized ionic liquid block copolymers for electrochemical applications if you're interested. So let me first take a break here and ask the audience a survey question. What is the most ubiquitous cation type used in ionic liquids? Ammonium, pyridinium, pyrrolidinium, piperidinium, or imidazolium? So the correct answer is imidazolium. So audience is not only listening to me, but they're really smart. So that's great. So let me transition now. So I'll just say a little bit about fuel cells. And so some of you may be familiar with fuel cells is basically a device that uses hydrogen and oxygen to produce energy and water as a byproduct and has been used in the fuel cell car here, the Toyota Mirai. And typically the way this would work is hydrogen would be fed in at the anode and oxidize on platinum. And the key here is really the separator. So typically Nafion would be used here as a sulfonated polymer, and it is an electron insulator proton conductor. And then on the downstream side, oxygen would reduce to produce water. And so this is, people are very familiar with this. And one of the downsides is the high cost because the oxygen reduction kinetics is pretty sluggish and requires platinum electrodes. So one alternative that folks have looked into is the alkaline fuel cell. And the difference here, the main difference is instead of protons going from the anode to the cathode, we have hydroxide anions moving from the cathode to the anode. And typically in the past, people have used liquid electrolytes. So the advantage of using alkaline fuel cells is that the oxygen reduction kinetics are very different in basic environments, and you could use non-noble metal catalysts such as nickel, so that's a huge advantage. And the downside is when you use liquids that have mobile cations and anions, such as potassium hydroxide, and you have any carbon dioxide in the fuel, typically you'll form potassium carbonate precipitates. And so the lifetime of the fuel cell is very short. And so this is why this has not been commercialized. But not very recently, within the last decade, it's been proposed that if we had a single ion conductor, particularly a polymer membrane, like an anion exchange membrane, we can circumvent this problem. And so there's been sort of a search for chemistries and materials that could solve this problem in this field. And so here I'm just showing you on slide 24 some examples, some chemistries that have been introduced. And some of the things you may notice is that many of the chemistries are ammonium-based as the covalently attached cation. And what some investigators found early on is that these chemistries degrade pretty rapidly in an alkaline environment through E2 elimination or Hofmann degradation and nucleophilic substitution or the SN2 mechanism. So to combat that, a number of well-known groups have looked at some more exotic cations here. I'm just showing some examples and looked at the chemical stability and tried to improve that for this application. We were interested in ionic liquids. And so here I'm just showing you an article that shows the reversibility of the imidazolium when you hydrate and dehydrate it to a carbene. And people have shown that you can isolate these carbenes and they're fairly stable. And this is to be contrasted with the ammonium-based chemistry where if you hydrate or dehydrate, you could irreversibly form ylids. And so in fuel cells, hydrating and dehydrating is a huge issue. And so this just gives you an example of why you may want to go away from ammonium, and the imidazolium may be an option in alkaline ionic liquids. And here's just an example of several folks who have isolated alkaline, so the hydroxide is a counterion ionic liquids, and they were fairly stable. So one question we had early on was, could we produce polymerized ionic liquids where the counterion is a hydroxide or an alkaline polymerized ionic liquid, and how would these fare for this application? And so here's one example of one that we synthesized in our lab. Here's a hydroxide counterion, and this is just a proof of concept here. So we're showing conductivity as a function of time in the red data, and we're showing our condition change from 90% over time to 10%. So you see the conductivity drops, but then over many, many hours we can recover that conductivity because remember, this is a water-assisted process. So For an ammonia-based chemistry, you wouldn't be able to recover this conductivity. So this demonstrates that stability under hydration cycles. And then we followed up and we just did a lot of NMR on this, and we showed that under certain conditions, this is stable, but under other conditions, you can get it to be unstable, and you can see ring opening of the imidazolium, and also for this particular backbone, you can see some hydrolysis as well. Let me take a break here and ask another survey question. I like trivia questions. Alkaline fuel cells were used on which NASA space missions? The Apollo program, the Gemini program, the Mercury program, the Space Shuttle program, or the International Space Station program? The correct answer is the Apollo program, which is the same program that sent us to the moon. You can see here's an actual picture of one of the fuel cells used in the Apollo missions, and this is a picture taken in the Smithsonian Museum here in Washington, D.C. So remember, next time you're in Washington, D.C., please look at the Air and Space Museum and check out the actual fuel cells used in the shuttle programs. Also, the PEM fuel cell, which I showed earlier, was also used on the Gemini program, and you'll see that there too. In my remaining time, I'll just highlight a couple key features about polymerized ionic liquid block copolymers as it applies to alkaline fuel cells. I'll just show a couple of results on, again, how transport and morphology are intertwined, and just make a couple comments about alkaline chemical stability for this application. You know, one of the things that we did was just did a controlled study of making a block copolymer or random copolymer at the same exact composition and charge density. And we made block copolymers here using the raft procedure, and we made random copolymers using free radical polymerization. And you can see here, as we would expect from a block copolymer, you can get phase-separated morphologies. At this composition, we saw a lamellar morphology, and with the random copolymer in the small angle X-ray scattering, you see no defining peaks, so there's no structure at all. And here's just a TM confirming this lamellar structure. So we have these conductive channels in the block copolymer. And sort of as I expected, if you plot the conductivity versus inverse temperature at a high humidity for the block copolymer in blue and the random copolymer in red, you can see a significant difference in the conductivity, and that's due to that nanostructure. So all things being equal here, the only thing difference is the morphology type. So same charge density, same water content, everything. And also another interesting feature here is that the block copolymer is actually a little higher at this specific condition than the homopolymer, even though the homopolymer had a 3 times higher charge density and more water. Morphology has a big impact on this. And for us, from a practical application, this polymer under dry conditions actually had 2 high glass transition temperatures for the block. So it's actually very difficult to make films and stamp electrodes on each side for a fuel cell application. So one thing that we did, and we've done a number of things, but here's just one example of just increasing the chain extender here from 2 to 11. And you can see here, now the polymerized ionic liquid block has a lower glass transition temperature, and here you can make some flexible films and stamp electrodes on both sides for fuel cell testing. And this just gives you one example of many different things that you could do, lots of different versatilities in chemistry that could have a significant impact on the physical properties of the polymer. And then here's morphology of one of these, just shows phase-separated morphology and also increased conductivity due to that morphology change. And so here's one of our membrane electrode assemblies, and here you can see fuel cell results. And from this study, we basically learned that it works, which is great. However, the fuel cell performance could be improved pretty significantly. And probably the one thing that caught our attention was the lifetime was not great. So some of the in situ, ex situ chemical stability still, I think, needs to be worked out in this entire field. But I think the imidazolium, the specific chemistry we were looking at, was probably not chemically stable enough for the actual fuel cell application. We sort of have followed up, and many people now recently have followed up to look at chemical stability for this alkaline fuel cell application. And I'll just wrap up with a couple comments about that. And so when we look into literature, we noticed a couple different things. Most of the literature that we saw on this specific field would do chemical stability of small molecules, and then from that suggest that that would be good in a polymer setting. And so what we wanted to do is see if that hypothesis was correct. So we want to do a study where we look at small molecules and polymers in tandem. And many studies that we saw only would look at one polymer backbone and one cation. So what we wanted to do is look at many cations on the same backbone and many backbones with the same cation. We also noticed in the field that their degradation conditions vary. So what we want to do was have something very constant. So we held the local concentration or the equivalence of hydroxide the same. And then also some of the conditions we saw were not very applicable to fuel cells. So some people would use non-aqueous solvents. So we wanted to mimic fuel cell conditions a little bit better. So some of the things that we thought of when we did our study, and I've noticed a number of other groups have done similar things as well. So here's just one example of looking at multiple cations on the same backbone, different imidazoliums, ammoniums, guanidinium, peroxidinium, phosphonium based. And sort of this is just a summary. So we looked at this at 20 molar equivalents, potassium hydroxide, 80 degrees Celsius for a week. And you can see the imidazoliums, as we'd expect, are better than ammoniums and phosphoniums. But here we saw peroxidinium base was actually much better. And we also found that there really was not a clear correlation between small molecules and polymers. So the environment of the polymer and the linkage of the cation to the polymer plays a significant role in the chemical stability, something I think should be noted. We also looked at different cations on different backbones. So here's a sort of PMMA type with a long extender, acrylate with a long extender, and also styrene based. And here's just sort of a summary. So we found in all of these the peroxidinium was by far the best cation. And you can see on the styrene, we saw the best chemical stability. We actually saw no degradation under these conditions. So we found something pretty simple to make, not very exotic, with high conductivity, very reasonable water take at high ion exchange capacities, and no, under these conditions, really high alkaline chemical stability. So now we're incorporating this into block copolymers, and our preliminary results show much better fuel cell performance. So that was very encouraging for us. So to just conclude, hopefully I've shown you that polymerized ionic liquids are a new class of ion-containing polymer which captures the unique physiochemical properties of ionic liquids within a macromolecule, which is very interesting for a number of electrochemical applications. You really have the potential to synthesize a vast array of new PILs. It's almost limitless with numerous IL cations and anions available. And probably many applications I haven't touched on here is, again, you can incorporate these into a lot of plastics. For coatings, I've seen in industry, for additives to oil and things like that, which I haven't touched on in this. Also, PIL block copolymers can join the benefits of both ILs and block copolymers. And these can be utilized as robust membranes for fuel cells, batteries, and also other applications. Thank you. I'll hand this over to Mark.
Joe, thank you very much. Outstanding. I am going to be fielding questions that have already come in through the GoToWebinar interface. Please continue to send those questions. I'll get to as many as I can at the end of this. Please also remember to mark your calendars for the tentative dates for the upcoming two other webinars in this series, July 25th and November 14th. Speakers are yet to be determined, but we'll come back to that at the end. I'm not going to say much more except to turn it over to Thomas Epps at Delaware, who's going to give us the second half of the webinar. Thomas, please.
Thank you very much, Mark. And so what I'm going to do today is just tell you a little bit about the second half of the power of plastics. And in particular, I'm going to talk about nanostructured plastics in polymers and batteries. I'm going to focus primarily on the electrolyte, but also allude to some of the other areas, in particular the electrodes, where polymers and nanostructured materials might play a role. One of the first things just to think about here is that when we think about battery technologies, there's obviously a variety of choices that I have, but in particular when I look at lithium-ion batteries, they offer some considerable advantages over traditional batteries such as nickel metal hydride and lead acid batteries, in particular due to their high energy density, both in terms of by mass and by volume. In addition, the lithium-ion batteries also have high open circuit potentials, they have low self-discharge rates, and minimal memory effects, all of which that make them advantageous for a variety of different applications. Now here I'm just showing very briefly some of the applications. You can obviously envision many more, but when we look at this slide, one of the key things that's apparent is that I've got an electrolyte, and then I also have a cathode and an anode. And they're all challenges associated with each one of these components, and as I mentioned, what I'm going to focus on primarily is basically that electrolyte and its performance and how we can use nanostructured polymers to actually tune that. Think about this, as I mentioned, we've got an anode and a cathode and then the electrolyte / separator. So in this particular case, then what we can get is we can get basically our discharge cycle where we get lithium migration from the anode to the cathode. We can actually do charging again. And one of the issues that's associated with charging is that we can actually get dendrite formation, which can lead to some of the failures and issues associated with batteries. So we're all aware of those types of things happening. So for example, here's one example of dendrite formation, basically showing that I can get a lithium metal dendrite that can actually propagate across a typical polymer-based electrolyte. We've all seen instances of this in the news media. So for example, with the Boeing Dreamliner, with the Samsung Galaxy Note 7, and then also with some of the issues that have come up with things like hoverboards, etc. One of the things that we want to discuss is how can we actually improve the performance, the reliability, and safety of these materials, and how we can use macromolecules to do that. So our key discussion goals that I'll talk to you about are how we can use macromolecular architecture design to improve battery materials performance. I'll also discuss how we can use nanostructured materials to overcome competing battery performance constraints without elaborate processing. So obviously, and just to expand on the second one a little bit, one of the things that you really want is you want something that's a high-performing battery, but you also want something that's going to be mechanically stable, thermally stable, and also has a nice long lifetime. And one of the key things that I want to touch on is how you can use in situ and complementary characterization tools in order to optimize materials design and why that's important for these types of applications. So when we think about nanostructured polymers, we can initially just think about sort of that archetypal material such as PSPEO. And so one of the ways that that works is I've doped that typically with a lithium salt. And what I have is basically that lithium ion that hops along that polyethylene oxide backbone, and that gives me the transport that I need to have reasonable conductivity. Now I do unfortunately have a trade-off. And so that trade-off is basically shown in this plot in the upper right, where I have that trade-off between ionic conductivity. So as that typically goes up, then my mechanical strength goes down. And so what that typically is going to mean is that I'm going to have problems with long-term stability in dendrite formation. And what I'd ideally like to do is I'd ideally like to achieve independent control over that conductivity and that mechanical strength. And one of the ways that I can do that is by forming things like nanostructured polymer electrolytes. In particular, one of the key metrics that people look at is that can I get electrolytes that actually have high modulus of the order of 7 gigapascals, which has been desirable to prevent dendrite formation. One of the ways to do this is actually, as Joe introduced very nicely, is using block copolymers. So in this particular case, we're going to start out talking a little bit about the archetypal system, which is basically a polystyrene polyethylene oxide. And one of the reasons for that is as follows. So again, what I want to have is I want to have an electrolyte material that's able to basically conduct ions. So in this case, polyethylene oxide is a very good material for that. It's got a reasonable ion conductivity and a low glass transition temperature, which helps facilitate ion motion. One of the difficulties with this material, though, is that it has a relatively low shear modulus, and so it's not really the most mechanically stable material. So what I can do is I can basically combine this or block it with mechanical support material, something like a polystyrene, which gives me that mechanical stability, and in particular that modulus that's very close to that 7 gigapascal limit. And the first part, what I'm going to talk about is basically salt-doped polymers, and in that case what you need to do is you need to take this polymer and actually dope it with a lithium salt so that I have the lithium available for lithium ion conductivity. So typically how that works is I take a block copolymer. What I'm going to do is I'm going to find some way to add that salt either through co-dissolution, and that salt's going to do several different things. It can change the morphology, It can segregate into one domain versus the other. It can lead to transient behavior in terms of glass transition temperatures, and it can also then influence the processability of the materials. So what's the archetypal system and where did this all start? So it started with polystyrene polyethylene oxide. I've already talked a little bit about that chain motion assisted diffusion, but one of the things that I want to illustrate is basically shown in the right-hand plot on this slide. So basically what you're looking at is conductivity as a function of temperature. And so what you can see is that I get reasonable conductivities around about 1 × 10⁻⁵, up until I get back down to about 60 degrees Celsius, at which point I see a discontinuity in that conductivity. So what's happening there? So one of the things that we can do is we can actually go look at DSC data, and we see that we get melting and crystallization of that polyethylene oxide domain in those PSPEOs. And upon crystallization, I essentially arrest or significantly retard chain motion, which means that I get no lithium ion conductivity. And you might say, well, why is that important? So for example, if I'm operating a material that I want to use in, say, a car, for example, operating in this range is reasonable and I can deal with this particular polymer system. However, if I want to use my laptop or cell phone, for example, and many times I want to be around temperatures about 20 to 40 degrees, and so this conductivity down here at 1 × 10⁻⁹ is completely unacceptable. So one of the things that people have looked at is how can I actually get rid of that crystallization? And one example is just to, instead of having that polyethylene oxide, is to actually use, say, a methacrylate-based material, very similar to some of the materials that Joe talked about with the ionic liquids. And then in this case, what I've done is I've actually taken those ethylene oxide repeat units and moved them from the main chain to the side chain. By doing that, what you can see, first of all, if we look at the DSC data, the calorimetry data, is that I've actually eliminated that melting and recrystallization behavior. Now, given that, what I can see when I look at the conductivity data is I now have a system where when we go to lower temperatures, what you can see here is I no longer have that discontinuity, and so I now start to have materials that are potentially useful for more room temperature type applications. Before we get further into some of the unique chemistries and the material architectures, I also want to give a nod to morphology considerations and processing behavior. So one of the things, as was mentioned in the previous talk as well, is that it's important to understand the impact of the nanoscale structure on performance. So in this particular example, I can have things like lamellar structures where I can get conductivity in, say, 2 dimensions if I'm looking at conducting the blue dots through the blue domains. But what I can also do is then I can start designing 3-dimensional networks, for example, where I have conductivity in all 3 dimensions. So what are some of the advantages of these network structures? First, one of the advantages is that basically I don't have to do any post-processing alignment for these materials. And so that's quite nice. The second thing that I typically get is I get improvements in mechanical strength, typically due to the fact that I have this network-like structure that has some significant mechanical integrity in 3 dimensions. So here's just one example from our group on basically some of these processing effects and why it's important to have 3-dimensional connectivity in these structures. And so in this particular case, what we did is we actually did, one of my students actually did a very tedious experiment where we essentially made a polymer disc, and he essentially sliced it into a bunch of sections as shown here. We did a sandwich cell geometry to actually look at the conductivity, and then he took those slices, actually rotated them 90 degrees, resealed the sample cell, measured the conductivity again, rotated the sample cell, or the samples 90 degrees again to 180, and actually remeasured the conductivity. So why did we do that, and what did we see? One of the first things that we saw, again in a PSPEO material doped with a lithium perchlorate salt in this particular case, and what I'm doing and what I'm showing here is basically the conductivity at a given angle normalized to the conductivity of the initial sample at 0 degrees. So obviously then what that means is that the 0 degree sample is at 1.0. And what I'm showing over here on the right side is basically we did in situ small angle X-ray scattering and actually were able to calculate the relative fraction of lamellar grains that were oriented either perpendicular to the direction we were conducting, which is up and down, or parallel to the direction that we were actually conducting the lithium ions. So in this bottom case here, basically slightly above 80% of our material was actually in a direction that didn't promote conductivity. Now what you can see when we actually take the sample and we rotate each individual sample 90 degrees, and again we do that in situ sacks, we see that now we have samples that have about 80% orientation in the conducting direction, and what we can see is that we actually increase the conductivity by a factor of about 2.5. Now you might say, well, is that just a feature of you cutting the samples and manipulating the samples? But when we actually do 180 degrees, so we flip the samples again so they're now back in their original geometry, then what we see, we actually go back to baseline. And so that's just a quick little story about how processing and the fact that we've actually sandwiched and processed these materials in order to make them does put inherent bias in that nanostructure and leads to differences in conductivity. So how can we get around that? So in this particular case, what we've done is we've made another sample. This is a cylinder-forming block copolymer, but in this particular case, the blue is actually the conducting domains. And so what you can see is that the blue domains are actually co-continuous through the material. And so basically, if I look at now 0 degrees, if I rotate it 90 degrees or 180 degrees, I see in all cases my conductivity is nearly identical. Again, it's at 1.0, but I will note that that's because we've normalized it to the 0 degree point, but this conductivity is actually about a factor of 3 higher than the conductivity that you saw on the previous slide. So by incorporating basically a co-continuous structure, not only have we improved the conductivity, but we also have been able to eliminate processing effects in these materials. So I want to take just a quick break and ask an audience survey question. And that question is, what are the key structure property features of nanostructured polymers in improving electrolyte performance? Just as a quick note, there may be more than one correct answer. And the choices are reduce risk of catastrophic failure events through incorporation of mechanically robust components, increase conductivity by decoupling transport from structural stability, increase processing through processability through self-assembly, or none of the above. All 3 of those choices, obviously not the none of the above, but the other 3 were actually all correct answers. One of the things that I'd just like to mention is that are there sort of alternatives to the salt-doped polymers? Because you can start to see that we can have some increase in conductivity, but these materials aren't necessarily ideal. If you looked at or noted the conductivities in the previous slide, we were at on the order of about 10 to the -5 Siemens per centimeter, and we'd like to be able to get higher, also improve the mechanical stability and the processability of these materials even further. So as a couple quick examples, there are things like bottle brush polymers, where in this particular case, I've essentially got a backbone, and basically what I've done is I've essentially polymerized my 2 blocks as brushes as side chains. Now, one of the nice things about these materials is that they retain some of the behavior in terms of the performance or conductivity of higher molecular weight systems, but they're inherently more processable due to their lack of entanglements. So this data shown here on the right is just one example from the Grubbs group, where they were able to actually get conductivities up to about 10 to the -3, but more importantly, they were also able to use the system to suppress crystallization, especially at the higher salt loadings, so on the order of 10 to 1, 5 to 1, and 2 to 1. Additionally, so one of the issues with these systems and one of the areas that can lead to further improvement is it's very hard to get things like network nanostructures from these systems, and so there's opportunity for actually designing new bottle brush polymers and other systems that actually have these co-continuous pathways. So as another example of innovations in this area are things like tapered block copolymers. And so this is one area that we've been focused on in my group. And so just to show an example of what tapered block copolymers are, basically what I've got is I've got block A, block B, and what I've done is I've actually put a compatibilization region of a mixture of the A and B segments between those two homopolymer blocks. By doing that, what you can see is just some of the differences that you can get in phase behavior. So for example, the non-tapered or traditional block copolymer forms things like lamellae and hexagonally packed cylinders, whereas by putting in different types of tapers, you can see things, well, you can see two key features. One of the first things is that as a function of salt loading, I see that I actually get disordered phases at lower salt loadings, but as I increase salt loading, going from left to right, that I get a variety of nanostructures, including things like this triply periodic double gyroid structure. Now, if I move to the inverse taper, which is basically just an opposite or different type of taper, I can see that disordered region lasts longer. I won't go too much into the reasons why, but the key thing to think about is that we're actually decreasing the segregation strength or improving the processability of these materials. Not only are we able to improve the processability and tune the morphology by using the tapers, we can also do things to actually tune the conductivity. So in this particular case, what I'm showing is the example of that normal taper. So the blue colors here actually correspond to each other. And basically what you can see is that by putting in that tapering, we're actually able to get higher conductivities than we do in both the neat material, which is shown in red, as well as than just the typical PSPEO material, which is shown as the black symbols. Now, why is that? And so the first part is just a summary of what you already saw before, both in terms of not only the self-assembly, but also one measure of the interactions between the systems. On the right-hand side, basically what you're looking at is the conductivity here, and now the explanation for it. So as Joe mentioned in the previous talk, glass transition temperature is very key to the transport and conductivity in these particular systems. So this is just one example here, where now you can see in that blue curve, which was again that highest conducting sample, we actually were able to measure the lowest glass transition temperature, whereas the sample in green that had the lowest conductivity of the three tapered materials, it actually has the highest TG. So again, just providing that link between glass transition temperature and the transport behavior in these systems. Now, a couple other things that I just like to mention in these particular systems are people have looked at several alternatives, which basically include different types of systems like polyisoprene, polystyrene, polyethylene oxide analogs, which are able to form different structures such as O70 or orthorhombic networks. But in these particular cases, they actually contain cross-linkable groups that were able to basically lock in morphologies and then allow the incorporation of both ionic liquids and or lithium salts that could then promote conductivity without sacrificing some of the morphology. Now in this example shown here, we also see an example from, in this case, from the Hillmeyer and Lodge groups, where basically they were using a polymerization-induced phase separation process. One of the nice things about this is that they didn't actually have to make a traditional block of polymer. They actually used a polyethylene oxide as basically a seed material, and then they used a styrene divinyl benzene mixture, which was able to polymerize off of that polyethylene oxide and phase separate simultaneously, which allowed them to form a very nice co-continuous structure. Even though it didn't have long-range order, it still showed an increase in performance in terms of conductivity. Now, one of the final systems that I want to mention for this part of the talk is that basically others, such as Lyndon Archer's group and Jeff Coates, have looked at things like cross-link PEO-based systems where they were able to do a couple different things. They were able to get reasonable conductivities on the order of 10 to the minus 4, but I do want to note they had a relatively low shear modulus, about 10 to the 5th, so not quite close to that gigapascal limit. However, one of the things they were able to find in these types of systems is that they actually had improved short circuit times, meaning that they were able to resist some dendrite formation even without having that high modulus material. So one of the things I just want to point out there, even though there's some well-established rules in terms of having a high modulus system, we may find as we do more work in the nanostructure systems, that's not exactly hard and fast rule. So one of the things I want to mention is that these systems are great. We've doped in a salt, so we have an anion and a cation, but there's some potential issues. And one of those potential issues is that I need to consider my counter-ion motion. And so in this particular case, one of the things that I need to consider is that basically I can get ion pairs or ion triplets, for example, such that most of my lithium is either bound and doesn't move, or I get countercurrent flow of the anions. And so when I think about that, all that's going to do is actually reduce my performance of my material and also potentially lead to charge polarization. So one of the things to think about, as alluded to in the previous talk, is what if I use things like single ion conductors as a potential solution? And so here are just a couple examples of some single ion conductors, just highlighting work from Anne Maze's group, from Michel Armand, and from the Garibaldi groups. And in each of these cases, in this first example shown here, this was a very nice example where they went through actually changing the block structure. So in this case, this single ion containing block was actually moved around in the block copolymer. And by doing that, they were able to isolate that having a separate or segregated domain of that ion, that single ion containing polymer was essentially the best in terms of performance. Now, in all of these cases, what they look at is not just conductivity, but transference number. And what does that mean? So just really briefly, what I'm looking at in transference number is I'm really interested in the motion of lithium, which is the ion that's of interest. And I have to be very careful when I think about conductivity, because when I'm actually measuring conductivity in many cases, I'm not just measuring the lithium, but I'm also taking into account the anion that is moving also. So these potential solutions where the anion is tethered to the polymer chain here, here, and also in these cases, and now only the cation is mobile, is something that can really allow me to improve the performance of my materials. So in the last couple slides, I just want to mention a few things. So one is that these materials that I've shown here end up being quite synthetically challenging, right? So they're not as simple as just a conventional PS/PEO or even some of the brush materials that were shown previously. Now I can move to other types of systems where I don't necessarily have a single ion per se, but I can start doing things like where I dope with a lithium salt here, in this case lithium TFSI. But what I've done is I've actually included a polymer block that actually has hydrogen bonding groups that hydrogen bond with that anion. So now when I hydrogen bond with that anion, I have the lithium ion that's mobile, and I effectively have introduced a single ion conducting character to these materials. So again, this is one case where I can get transference numbers that are up above, say, about 0.7 in this particular case. And just to contrast that to PS/PEO really quick, I typically get transference numbers of about 0.2 in PS/PEO, meaning that the majority of that motion that's giving me rise to the conductivity in those cases is not the lithium. So here's just a couple other examples where in this case now I can, instead of using a PEO-based system, I can use a PFPE, so a fluorinated ether-based system. And again, in these cases, basically what I'm doing is I'm changing my system such that I can essentially immobilize or tether that anion and promote only cation motion. And at the bottom shown here is basically another example, in this case from the Balsara group, where now they've made big salty nanoparticle anions, again to try to restrict that anion motion. I want to just introduce one more survey question. In this case, the question is, what are the advantages of single ion conducting systems? There may be more than one correct answer, but your choices are, do they limit energy needed to conduct lithium ions? Do they reduce charge polarization? Do they reduce synthetic complexity, or none of the above? So the answer there is the first two choices. In most cases, the single ion conducting materials actually increase the complexity. And one of the reasons for that is because the monomers, if we look at the structures, are actually a little bit more difficult to make. And I typically have to use, in some cases, some more specialized polymerization processes in order to actually make those polymers. So the answer is the top two. So in the last couple slides here, I just wanted to point out a couple key features that can't be overlooked. So one of the things is we've talked a lot about some of the experimental tools and experimental efforts, but it's important to say that the theory cannot be overlooked. And in particular, some of the links between theory and experiment can be used to do several things. So in many cases, when I look at these systems, both in my talk as well as in Joe's talk, then you saw sort of that complexity. I've got morphology, I've got ion motion, I've got anion motion, I have processing conditions, I also have then my actual operating conditions. And so to be able to extract the important parameters, links to theory are actually very important. And so I can start doing things in particular for battery applications, like once I've doped these materials with salt, I can use things like theory to actually, in this case from Juan de Pablo's group in coarse grain simulations, to actually get out the density profiles in the polymers. And basically you can see in this little red line down here how the anion and cation density profiles mirror that of the different block copolymer domains. I can also do things like study phase transitions as a function of salt concentration as shown here. And I can also then elucidate some of the differences between homopolymers and block copolymers and understand things like the importance of N groups, which actually turn out to be very important in controlling the ion diffusion in systems. And so this work is from Zhengdong Wang's group and then Venkat Ganesan's group at Texas. So the last thing that I'd like to mention is basically I can also do new characterization tools. And so one of the things that I can do is actually match some of that theory with new experiments. So here's just a couple key examples where I can do things like get density profiles from energy filtered TEM as shown in the upper left. I can also use things like XPS C60 to get density profiles again and basically locate where my ions are in my nanostructured domains. And one of the things that's become a bit in vogue recently is actually using things like X-ray reflectivity or neutron reflectivity, again, to extract density profiles. And as you can see in the bottom right, that density profile looks very similar to the theoretical simulation work from de Pablo on the previous slide. So I want to just have one slide to mention that I've talked a lot about electrolytes, but there are also opportunities for nanostructured polymers and electrodes. And so, for example, they can be used as binders. And here's some of the requirements that are needed, just the high electronic and ionic conductivity, mechanical stability. I can also use them as sacrificial templates for electrodes, where I need an etchable component and then a very nice, phase-separated microstructure. Or I could potentially think about using nanostructured polymers as electrodes themselves. In this case, then these polymers typically have to be redox active. And just one example of a potential material that has electronic and ionic conductivity is shown on the right side, which is a P3HT PEO-based block copolymer. So with that, I'd like to conclude and just say a couple key things here. So basically, block copolymers or block polymers and other nanostructure forming systems allow us to really decouple mechanical properties and battery performance, which allow us to then attain materials that have improved performance, but also incorporate safety, stability, and lifetime. We can also look at the fact that co-continuous nanostructures, either formed through periodic block copolymer arrays or other methods that actually lead to co-continuous nanostructure formation, enhance transport and mechanical performance, and more importantly, they are moved with an eye towards the actual processing and processing impacts. One of the things that I'll mention is I did talk about two approaches, so salt-doped materials and single ion containing materials, both with opportunities for improving transport. But I also want to mention it's important that we don't forget the in situ and complementary characterization tools, as well as then the links between experiment and theory. So with that, I'd just like to acknowledge some people that did the part of the work that I showed related to the Epps group, and in particular in green, Melody Morris, that assisted with the putting together this presentation. So thank you very much.
Thomas, thank you very much for a second outstanding presentation. We're getting a lot of questions here online, and so I'm going to do my best to answer as many as I can. I think what I'm going to do, Joe, if you're ready, is go back to Joe's presentation while some more questions come in on Thomas's, ask you a few questions, and then jump back and forth. Joe, here's a question from Elizabeth. She's interested in how the glass transition temperature of the backbone polymer, how that can have a significant effect on ion conductivity in both homo and block polymers. You focused mainly on the methacrylate backbone. Do you have any comment on how that influences ionic conductivity?
So, I mean, typically just the glass transition temperature of the polymer scales pretty well with ion conductivity for these dry conductors. So basically what Thomas had in his presentation and the ones that I had with the fluorinated counter anions, they'll typically scale with the glass transition temperature, and you could also scale the conductivity as a function of temperature with sort of this WLF or VTF behavior. And what we found with the polymerized ionic liquids in particular is that those parameters that you can regress from that model, you can actually see that they have a higher free volume than many typical polymers that you would see out there. And there's quite a bit of literature now on showing why they have higher conductivities at low temperatures compared to other ion-containing polymers is due to that high free volume.
Great, thanks. Christopher would like to know, Joe, there's some limitations to stability. How much is that attributed to the kind of the acrylate ester linkages in the backbone?
For particularly the acrylate typically hydrolyzes pretty rapidly. Methyl acrylate, the PMMA type, that minimizes that hydrolysis, but we still see a fraction of that is due to hydrolysis. But we also see the primary mechanism for the imidazolium, even on a PMMA backbone, is ring opening before we start seeing the hydrolysis. When you switch over to the styrene, you're not going to see that. However, there are things that we predicted that didn't happen. So if you put a imidazolium on a styrene, it degrades very rapidly, whereas if we put a peroxidonium on there, it doesn't degrade at all. And so there's still a lot to be understood in terms of backbones and linkages with some of these cations.
And then Hyung Sun has a question about ATRP. Are you typically using ATRP, and can you get high conversions with ATRP and get narrow molecular weight distributions? Is that a common technique for making these?
ATRP is a technique that's been used for polymerized ionic liquids and can be used. In our lab, we like to use RAFT, but as I showed in the presentation, polymerized ionic liquids have been made, and block copolymers have been made with a variety of different techniques, and very successfully so.
Thank you. Thomas, I'm gonna come back to you, Joe. This question's pouring in. So okay. Thomas, I'm gonna go to you. This question comes from Walter. How realistic is it to use PEO as ionically conductive material in real life applications, since we know PEO can be easily oxidized? Is that a liability in these PEO-based materials?
In most cases, no, that's not a significant liability. We've been able to actually cycle these quite readily in things like coin cells and even a little bit scaled up systems, and have been able to see very nice stability of the polymers up to, say, 500 to 1,000 cycles, which is actually quite reasonable. Now, one of the problems with PEO, and typically what people are still doing, are seeing things like, can I dope in either ionic liquids or other types of groups to try to improve that native conductivity of the PEO-based systems? In those cases, I think the jury's still out in terms of how they behave with long-term stability. So I would say for the neat PEO systems, they're pretty good under most conditions, but when I start putting in additives, then I do have to worry about that.
I see. Christopher had a question about tapering. Would tapering in an ABA triblock copolymer have an effect on the compatibilization of that copolymer in a matrix of a homopolymer? Would it make it better or worse? I think the idea here is that tapering has some beneficial effects, but what about in composites with a homopolymer? What's your view on that?
Yeah, and so tapering is actually something that can be a bit ubiquitous in the sense that I can actually use it for a variety of things. So I am basically making a compatibilization agent that can stabilize an interface. And by putting in that taper, I've actually created a bit wider interface that can improve stability. So I know we've talked a lot about the polymer and battery materials, but it's also something that's useful in terms of surfactant-like systems for solution applications as well. So it's very true that I can use things, or even AB tapered polymers, as basically compatibilization or blending agents with homopolymers and other block copolymers.
Okay, thank you. Thomas, one more. So this is from Mark. High modulus materials can prevent dendrite growth, but then you showed some results about low modulus materials also doing that, and I think from the Cornell group. What's the current view on that? Do we need high modulus materials? Do we not? And if we don't, what is the attributes of a low modulus material that seem to prevent dendrite growth?
So I think that there's some room for speculation here. So when people have looked at basically that 7 gigapascal number, basically they've looked at the bulk modulus that's needed in a material to reduce dendrite growth. Now, what I can think about doing when I make these materials, and one of the reasons that both nanostructured as well as then these cross-linked PEO systems might work, is because now I'm not thinking about bulk dendrite formation, I'm actually thinking about dendrite formation off of a surface. And so by having sort of, instead of looking at bulk formation, looking at surface formation, I might find that I need a different or a smaller modulus in order to resist that initial formation off of the surface. So I would say that those experiments are a little bit difficult to do, but I think that the Archer group and others are going in the right direction when they're actually looking at inhibiting growth at a surface as opposed to actually focusing on the bulk modulus that's needed for dendrite formation.
Right, so interfacial phenomena play a key role here. Yeah, absolutely. Okay, I'm going to go back now to Joe's presentation. The questions are still coming in here, and got a couple from the last round. So this is from Mike. Joe, what about monomer synthesis? Is this an issue with respect to ease, cost, availability? So if one wanted to get into this from a more kind of practical standpoint, what are your views and experience with those kind of practical issues?
I think that's a great question. I think from an industrial perspective, I think some people are turned off by the idea of ionic liquids because if you buy them, they're quite expensive. However, synthesizing polymerized ionic liquids or functionalizing commodity plastics is actually relatively inexpensive. So I want to make that point. Probably the other point that's interesting is how you make this can really impact the way you characterize the material. So some functionalize the monomers to incorporate the cation and then polymerize the ionic liquid monomer, which is fine and it's pretty easy to do. However, sometimes it's hard to put a charged polymer through a GPC column. So an alternative method that a number of people are doing because of that difficulty is just to polymerize a bromine terminated monomer, put that through the GPC column, and then functionalize the material, the polymer, and create basically as your precursor, let's say like an imidazolium bromide, and then you can do an ion exchange metathesis.
Right. Here's a question from John. You mentioned a random copolymer control experiment, but John is wondering about dispersity. Could that also affect conductivity since it was polymerized using free radical or kind of normal free radical instead of raft, as I understand it? So can you make a comment maybe on dispersity?
It could. I mean, these are water. That specific example had water-assisted conductivity, but there could be, and I don't know if there is in sort of these water-assisted conductivity, if somebody has done a controlled study on PDI, but they are different in PDI. Raft, we typically get about, for those block copolymers, around 1.2 PDI, whereas the free radical will get around 2. So they are different, and that could be an effect, and I haven't seen a control study on that yet to see what that effect is.
Yeah, that's interesting. I wonder if it'd be interesting, if you had a distribution of chain lengths, how that might influence things where the low molecular weight chains may have a very different kind of influence.
Yep.
This is from Elizabeth. How about changing the counter ion and how that might affect the chi parameter for your block polymers and their phase segregation? You talked a little bit about TG and about hydrophilicity and hydrophobicity. Presumably that affects chi as well. Do you have a comment on that?
Yeah, and actually we do have papers on that, and other people do too. It will change it significantly. So that is another sort of tool that you could use, just the ion exchange reaction you could use to change the chi parameter and then change the morphology of the material if you were to solution cast after ion exchange. You know, there's different things you can do, right? So if you wanted to dissolve this in a solvent, do an ion exchange, cast the same polymer with different anions, you can play around with the morphology that way. If you want to lock in a morphology, you can also do a solid state ion exchange. Something to think about.
So Mark, if you don't mind, I'll jump in here really quick as well.
Please.
So that question applies also very much to the block copolymer systems that I talked about, in the sense that one of the ways that that chi parameter plays a role is it actually determines or influences the interfacial width between that phase-separated polystyrene and, say, PEO domain. And so what that does is, let's not forget that that polystyrene is a very hard or more brittle material, high TG material, and it's now connected to that soft material. So essentially the width of that interface, or the strength of the interaction between the PS and PEO, influences that PEO chain motion. So that's one of the things that we found in the tapered materials, is that by tuning the interfacial width, we're actually able to tune the glass transition temperature. So the link between chi and morphology and glass transition temperature, ultimately leading to transport, is a very important one.
Absolutely. Yes, thank you, Thomas. Let's go to some questions now, another set of questions for you, Thomas. This is from Marianne, and this is a little bit of a historical question. The thought is here that it seems like ionic conductivity has not really improved for solid polymer electrolytes in a couple decades. Do you really think we'll get ever useful room temperature conductivities for batteries using solid polymer electrolytes, and how do you respond to that?
Well, I think that there are a couple options. So one of the things that I didn't talk about, but what is a field that's sort of burgeoning these days, is using the solid polymers, but then turning them basically into more gel-like materials. And so there's work from the Lodge group and others where they've looked at not just taking that traditional PEO-based material, but taking that, again, putting in, whether it's glimes, other types of materials, low molecular weight homopolymer, putting in ionic liquids, and using that to really drive up the room temperature conductivity, and I can typically do that by several orders of magnitude. One of the other things I'll just mention is Joe pointed out in his section, and one of the listeners asked a question about, was, again, when I start thinking about costs. So I can start thinking about designing materials that have significantly higher conductivities, but then there is also the complexity of the synthesis and the cost associated with making those systems. So there is a little bit of a trade-off, but there's hope for sort of blended and more composite gel-type materials.
This question is from Christopher Thomas. Do the polymerized ionic liquids, or maybe even the systems that you showed where you talked about orientation, do they lend themselves to stress-induced orientation resulting in increased birefringence? Do you see any optical effects when you do these orientations?
It depends on the system. So the answer is yes, I can see that. And so one of the key examples are things that actually, for the two examples that I showed where I'm looking at lamellar or cylindrical structures, since they have anisotropic unit cells, I can actually see basically optical effects of that change in orientation. So just to point out, one of the things that we did is we actually, to make those samples where we're looking at the processing effects, we actually took samples and melt processed them under pressure. So essentially took a powder, melt processed it into a sample cell. So what we were doing is basically applying pressure or stress to that sample, and that was inducing those fractional orientations that we saw in those materials. So that, and the fact that they're anisotropic, we can in certain cases see alignment effects on the optical properties.
This is from Mark. Transference numbers are an important thing, especially when you're really more concerned about the lithium ion transport. This example you gave where one of the components of the block polymer binds with the anion, how would you compare and contrast that with a fixed anion that's on the backbone? Do you think both strategies have merit, and maybe compare and contrast them?
Yeah, so I think both strategies do have some merit. This gets back to some of the trade-offs. So in the case where I had the hydrogen bonding material, where I've got something that complexed with the backbone, I saw a transference number of about, actually it was 0.67. In the case of most strictly single ion conducting materials, that transference number is about 0.9. and we're talking on a scale from 0 to 1. So there is some difference. One of the challenges is the ease of synthesis. So many of these single ion conducting polymers are a little bit more challenging synthetically than basically materials where I can either take a conventional PSPEO, change the N group to get hydrogen bonding of the N group, or basically use PEO and take a commercially available monomer and polymerize off of that to get a hydrogen bonding moiety. So the question is, and it's still out there, does the benefit of having that 0.9 and the synthetic complexity associated with that outweigh the cost savings and the ease of synthesis that I have with a 0.7, so I don't get quite as high conductivity or transference number, but then I save money in terms of cost, etc. So there is definitely a trade-off there, but both are viable routes.
Right, I can understand that. There are going to be some questions I'm just not going to be able to get to, and I want to respect everybody's time. So I'm going to wrap up the question and answer session here. I really do want to thank Joe and Thomas for 2 outstanding presentations and for doing this inaugural Poly webinar. As the division chair, I really welcome your feedback and suggestions for improvements, suggestions for topics, suggestions for other speakers. You can feel free to send those to me directly. I hope most of you are members of the Division of Polymer Chemistry. If you're not, I've got good news, 2 pieces of good news. It's easy to join the Division of Polymer Chemistry. You simply send an email to Kathy Mitchum at Virginia Tech. That's kathyl@vt.edu, and your first year is free. So very easy is the first piece of good news, and your first year is free is the second piece of good news. I want to thank the presenters, all of the people who joined the webinar, and also the ACS for this.